Okay, good morning. I'm Ravindran from Institute of Mathematical Sciences. I work in strong interaction physics, just for an introduction, particularly in the context of Large Hadron Collider. And if you ask me specifically what exactly I'm doing, I'm working on what's called X physics. Okay, so I'm not very much connected to the kind of physics that is going on in EIC or going to go on in EIC. But I've been interested in this topic for a very long time, from the time of your age, actually, I would say, because I started as a researcher working on polarized structure functions. That was my topic of research. I hope you can hear me. Actually, it's not breaking. Okay. So that was my research topic, and so it is. It's like coming back to my area that I worked on during my initial stages of my research. So that way, I'm very happy to be part of this school, share some of the things that I learned over the years. So I will be actually hopping from let's say slides and board, because I know these days, slides are the most popular ones. I prepared something some time back, and I'm going to recycle some of them. So I'll not be only teaching using slides. I'll also go to board at some point, depending on the interest of people. So, and I also should thank the organizers, both Asmita and Bedango and Abhay and Marco, everybody who have been kind enough to actually invite me to this nice meeting to talk to you. Okay, so this is briefly the, it's not a brief title, but it's quite a big title. Okay, let me just move. Okay, here. Okay. Well, maybe I can use this actually. Yeah, that's good enough. Okay, so I'm actually sort of very optimistic to cover these set of topics and today and tomorrow. This is going to be my first experience to speak, 3 lectures in a day and so on and so forth. Okay, so let me try actually. Okay, I think she is to be blamed for that actually, but anyway, it's good. I can also exercise that. So these are the topics, and I'll motivate in the beginning why we are interested in this kind of physics at EIC, and what all we should know actually if you want to really sort of go ahead and study the physics at EIC. And these are the topics that we might require actually to understand. Okay, because it's a very long program in physics to understand structure of proton. Structure of proton is, for many reasons, is very important to understand. One, from philosophical point of view, because we want to understand what is everything made of. And another one is actually a practical point of view, because if you want to actually understand something else, we need to understand something that we are going to use it to understand. Okay, it's very complicated, but you'll understand actually why I'm saying this, okay, as we go along. Okay, so there's a reason why we want to understand the structure of proton actually. Okay, LHC physics is running very, very successfully simply because we have a very good understanding of the structure of the proton. If you don't know the structure of the proton, then LHC physics cannot be carried out. You can run the experiment, you can actually collect data, okay? But if you want to understand what is going on, okay, if you want to, say very confidently that we have seen Higgs boson, we need to know the, the physics of this proton that actually produced this Higgs boson. If you don't know what produced and how it produced, what made it to actually happen without understanding this structure, it's impossible actually. So in many contexts, actually understanding the structure of proton is extremely essential in high energy physics. Okay, so this is one of the reasons why actually EIC is being built actually to improve our understanding of the structure of the proton. Okay, so these are the topics. So let me just go over. So this question that we want to understand what are the fundamental building blocks of nature has been there for ages actually, from the time of Plato. And that time the answer was very simple, not very profound as you might think actually now. But of course the answer is unimportant to us. The question is very important actually. If we don't ask these questions, we cannot actually find anything interesting. So such questions really actually helped us to actually proceed and make a very long journey of understanding atoms and what is inside atoms, nucleons, electrons. And then in the process, we also managed to understand what proton is made of. We have, even my daughter tells actually what proton is made of quarks and gluons. So the answer that everybody knows today, simply because it's a long journey of studying this particular object actually. So strong interaction, of course, provides a lot of insight into the structure of the hadrons. Okay, and the earliest one was actually very profound and very important development that took place was during the time of Kelman through quark model, and then later on several of the scattering experiment actually provided information about the internal structure of the proton, and then there's the birth of Parton model, and then discovery of the dynamics through what we call now quantum chromodynamics. Actually, journey continues. Okay, so this is the plot that you may not be able to read anything from here, but I can see that there are plenty of measurements that came out from Large Hadron Collider, which has been running since 2000, beginning of 2010, 12, and so on and so forth. Actually, the large amount of data actually. Everything is trying to find out whether there is any deviation from standard model predictions actually. And the answer is actually more or less clear here from this huge plot. And I'm not showing to explain to you what LHC has done, but this is possible actually, that we could actually do a lot of measurements and compare it with the experiment theory to make very concrete statements that actually we confirmed standard model to very good accuracy. It's not possible without the knowledge of two things. One, the knowledge of the structure of the proton, and two, the computations that we do, okay, using standard model, okay, those computations actually, precise computations. So there are two eyes to actually to really actually come up with this. One was actually the understanding the structure of the proton. The other one is actually to understand the results that is coming from. Sorry. Yeah. Okay. Thank you. So there won't be any problem, no? Okay. So this is possible because this is for an advertisement actually, because we have a huge amount of results from LHC, and that confirms standard model simply because we have very good understanding of the structure of the proton actually. Of course, it's not complete. Okay, the formula that LHC, physicists use is this master formula. I don't know how many of you are familiar, but I'm going to teach some of the things actually in this course. Okay, so if you want to compute a cross section in, let's say, Large Hadron Collider for producing, let's say, a type of particle called A, okay? And this is the master formula that we have to use. It contains three different parts, okay? Two of them are actually called Parton distribution functions, which basically characterizes the, what partons that participate in in the scattering to produce this A, and what is the fraction of the momentum each of the parton carries from the incoming protons. And this sigma hat is the parton level cross section that basically tells you how these two partons collide and produce this particular type of object called A, or particle called A. For example, if you want to produce X, you need to collide two protons. From two protons, two gluons will actually come out. They collide and then make a triangle, a loop of top quark loop, and then that produces this X, because X cannot directly couple to gluons. Okay, and this cross section is computable, but this PDFs, these parton distribution functions, that actually carries all the information about the the probabilities of these gluons inside the proton. Okay, and that is not calculable. Not because it's not by some theory says that you cannot calculate it, but we don't have a technology to compute them actually using our theory that we know very well. Okay, of course there are efforts to actually calculate them on lattice, but that's also very, very difficult actually. So what they do is actually they extract it from some other experiments. What are the other experiments? The other experiments are actually experiments like tip inelastic scattering experiment. So if unless I understand this the PDFs, very, very accurately, very, very neatly, without too much of uncertainties, I won't be able to actually make predictions for this cross section, because this is computable and these are not calculable. So unless I know this from some other source, I won't be able to make predictions for producing this A in large hadron colliders. And the plot that I showed you, a lot of results actually agreeing with the standard model, really implies that we have very good understanding of these two structure functions Fs. Okay, and this was possible because of various experiments that I went on for the last few decades. Okay, and this is roughly the summary actually, that if you really want to make any nice prediction or any comparisons, you really need to know the structure of the proton actually through these PDFs. Okay, that's not the only thing that EAC is going to look at. There are also other aspects that other speakers would cover actually. For example, if I really want to extract this PDF from tip inelastic scattering experiments, okay, so you need to actually construct an observable like tip inelastic scattering cross section. Again, you use what you call this master formula, usually called the parton model formula, which relates this hadronic cross section to the partonic cross section through these PDFs. Okay. And by measuring this hadronic cross section and calculating the sigma hat from the theory, we can actually fit this Fs. Okay. So it's pictorially, this is what it means actually. This experiments like tip inelastic scattering experiments, actually with very high energy photons, which has a resolution, very high resolution, we can actually probe these things. I'll come back to this actually. This is one of the earliest experiments actually. I'm not talking about the earlier ones actually, but let's go look at the most recent in the sense actually in terms of the experiment that we have seen. Okay, HERA is the one which was running in DSE Hamburg in Germany, where actually there was a dedicated program to extract this parton distribution functions, because these parton distribution functions, of course, unravel the structure of the proton, and also it is also important for the future experiments to actually use it to study. Okay, and this is the one that is the topic of this program. Actually, that's physics studies at ELECTRON-ION collider, and it's really actually very nice that this program is going to come up, because it's not that we have understood everything about proton that we can actually carry on with our life, but we need to understand many more things actually, like the transfer structure and polarized structures and so on and so forth. There are many questions that we have not answered in the case of hadron. So this program is going to help us actually to understand. So this PDFs that I discussed actually, okay, we have a pretty good understanding of it actually. If you plot them as a function of the Bjorken variable x, they look something like this actually. These are not actually, calculated plots actually. You don't actually use your theory to, calculate them actually. These are extracted from the experiments that using the data and then the formula, you extract this actually. This is how it looks like. And similarly for other things like, C quark, gluons and so on and so forth, it looks something like this actually. This is just to give a feeling that, we are really after this kind of a functions, okay? And they carry very important information about the proton, okay? And what is the range of q square and x that we have seen so far actually? If you really look at, what Large Hadron Collider requires is something like this actually, okay? If you really want to do physics with Large Hadron Collider, we should really cover this entire region of x and q square of those PDFs. Only then actually we can use it and make sensible predictions or sensible comparisons actually. ERA and other fixed target experiments, the earlier experiments actually could probe only certain regions of x and q square, these two variables that these PDFs depend on. Okay, you can see you can go up to q square of 10 power 5, and then you can go to x, which is of the order of 10 power minus 5, and so on. And I understand that EIC is going to actually look at regions where x is slightly larger compared to what ERA could see, but that is the region where ERA missed many of the things actually. And similarly, the smaller q square regions where there may be very interesting physics hidden over there actually. So this is the kind of region that EIC is going to actually cover. Okay. So the task at hand is actually we have quite a lot of things that we need to understand. One of them is actually this PDFs. Okay, and I'm going to actually tell you how this is understood. So it is I try to convince you that it is important that we understand the structure of the proton. Otherwise, we cannot make progress. Okay, so a little bit about the history. How we have managed to understand proton the way we have understood today. Okay, so let's look at the earliest ones. We all know that observations reveal strong interaction is independent of electric charge. Of course, doesn't care about all the reaction that which are sensitive to strong interaction physics. Doesn't care about electric charge. It just sits outside as a overall factor. Okay. And another observation was actually it was proposed that strong interaction had a very interesting symmetry called SU2 isospin symmetry, which means that actually if you look at proton and neutron and look at all the reactions that we in strong interaction, you find that actually if you just interchange proton and neutron, nothing much happens actually. So that means there is some symmetry that actually allows us to treat both proton and neutron in the same footing for many cases actually. So this symmetry actually between proton and neutron actually led to bringing a concept from mathematics called group theory, okay, and that really helped us to develop our understanding of proton actually, as we'll see. Okay, so the symmetry that I talked about is isospin symmetry, which is called specifically a particular type of symmetric group called a special unitary group. It's a group of 2 cross 2 unitary matrices, and they're unitary, and it satisfies U dagger U is equal to 1, and it is special unitary. That's why this S here, determinant equal to 1. And in mathematician will tell you that this elements of this group can be parameterized as exponential of something with 3 parameters, because this is a group of three parameters actually. And the T's here are called generators of the group actually. And they are traceless because determinant of U is equal to 1. And they satisfy what they call Lie algebra, SU2. So this everybody is familiar. All we can say here is actually the states that we talk about, proton and neutron, they are immune to charges, electric charges. They transform in a particular way with respect to this, one of the generators of the group actually. If you T3, if I apply, this goes to, it goes to half of P, which means they are nothing but eigenstates of this. Once if you find that actually there is a symmetry between these particles, then you can actually interchange them and then you can make predictions for from one reactions to the other reactions. So that way actually people try to sort of classify the bunch of hadrons that they had seen in those days, okay, using various symmetric groups actually. Okay, so these are the symmetric groups. The same symmetric group actually was used by classifying several of the hadrons, particularly mesons in this case actually, to group them into classes where you can actually name them with triplets, doublets, and singlets, and so on and so forth, because these are different representations of SU2 group. And then some of them, they could actually put it in the isotriplets representations of SU2, and some of them, they could put it in the doublets, and some of them, they could put it in the isosinglet states actually. Okay? So this way, they could actually organize the hadrons that they had seen in those days actually. So a huge number of hadrons, like Mendeleev actually arranged elements in the periodic table. People could arrange these things using certain symmetry groups. Okay? All it says is actually, in summary, that the strong interaction had some underlying symmetry, okay, which you can translate to the facts like U, H equal to 0, or generators commute with the Hamiltonian, even though we don't know the form of the Hamiltonian. Okay, we roughly had some idea about how the potential looked like, but at that point actually there was no clear understanding of how the Hamiltonian looked like actually. Today we have a very good understanding of the Hamiltonian of strong interaction actually through QCD and so on and so forth. Okay, so all we knew actually, if there exists an Hamiltonian, that has to be satisfying these relations actually. Okay, so this also implies that the masses have to be degenerate. You can always go to a rest frame and then say that you have some relations among masses actually. And of course, life was not very easy. There were observations, experimental observations, which showed that actually the degeneracy was not exact. In the sense, the masses of proton and neutron, they were not exactly identical, but there were some differences actually. Similarly, for the mesons, which we could put it in one isotriplet, we could no longer claim that actually this symmetry is inexact because there is a mass differences between them actually. So if you just look at the mass differences, you find actually there are appreciable differences actually, which really tells you that the symmetry is not an exact. It's always good to have bad news, because this bad news translates to good news actually. So here, many of these observations that when they catalog these hadrons in this framework, actually they found lots and lots of deviations actually. Because of those deviations, people could make progress actually. Okay, so the small perturbations they want to understand, and then now we have understood that actually there are also other interactions between these hadrons which are responsible for actually breaking the symmetry. Okay, of course, in the process, people actually discovered new particles which they could not fit into the framework. Okay, and they call them actually strange particles. One of them is actually lambda 0, it's called baryon, lambda baryon. The other one is K. And these reactions actually, in fact, demonstrated that then you need to introduce new quantum number called strangeness. Okay, so introduce some, what you call discrete properties like, the strangeness -1. I mean, it's not discrete actually. There's a corresponding U1 group for this. So this is strangeness for lambda 0. You assign them, to -1. It's your choice. K0 + 1. And if you could do and show that actually that this reaction can take place, provided this strangeness is conserved. And you go on and actually make predictions and see whether this is a good quantum number or not actually. Okay. Of course, the observation revealed that weak interactions or other type of interactions do not respect the symmetry. Only strong interactions very special for this. Okay, and this introduction actually brought a new concept called hypercharge. Okay, so Gell-Mann and Nishijima actually, by studying large number of large variety of hadrons, okay, mesons and baryons, they came up with a very nice relation between charge, baryon number, and strangeness. These are the things that everybody is familiar. So, but they were all completely unrelated actually. Charge of a proton or a charge of a neutron, and their SU2 properties through T3, they were all completely disconnected actually to start with. And these two gentlemen actually made a connection actually that electric charge can be related to the the third component of the SU2, and the hypercharge defined by this combination of baryon number and strangeness divided by 2. So this is a very well-known Gell-Mann-Nishijima formula, and this formula could fit all those hadrons that they were known actually in that time. Okay, so you take any hadron, proton or a neutron, and look at what is the charge, look at what is the T3 value, eigenvalue of this T3, and then I find out what is its hypercharge. It was fitting very nicely. So this is some magic formula. Of course, there is a mathematics behind it, and it was working very well for most of the hadrons actually. Okay, and also they could actually use this T3 and Y, okay, of this hadrons that they had with large amount of hadrons, to put them in some sheet of paper nicely like this actually. Okay, all they need to do actually, they take two-dimensional plane spanned by this T3 and Y, and then just take a hadron, and then find out what is T3, what is this Y, put it on this plot actually. So you could put many of them actually in this, and they could actually show that 2 minus and 1 minus mesons and off plus, these are parities actually, this plus, minus and things like that, videos can beautifully fit into this octet representation of this I-dimensional representation of these groups. Similarly, for 3 by 2 plus could fit in the decuplet one, things like that. This was the birth of famously called eightfold way. So, okay, so they look more like the SU3 representations, even though they are actually coming from SU2. So SU2 was the the main group actually, but that I-dimensional representation of SU2 actually, the one that this what they've actually managed to fit in actually represented more like a SU3 representations actually. Okay, good. So this program went on. So we had many predictions, and then they could fit into this setup actually very nicely. So this is how hadrons were classified in those days actually. Okay, so discovery of this particle omega minus, and that was was at the predicted value with the correct decay properties, and important evidence for convincing large segment of physics community that the classification using this symmetric group is the right way to go about. And we have convinced, and it's now become a textbook material actually. So the eightfold way scheme proved that the fundamental representation of SU3 is not identified with the known particles. The significance of the fundamental representation of SUN is that the higher dimensional representation can be built out of the tensor product of fundamental. So this statement actually is not very difficult to understand. All I'm trying to say here is actually it's not that you look at the fundamental representation of SU3 and put 3 hadrons in it, and then that you call actually is the way to go about it. But what this program actually demonstrated was actually representations of the group actually nicely are nothing but this this zoo of particles that we see actually. So different representations actually put this zoo of particles into different classes actually. So this is not, they are not in the fundamental representation, but they are in the high dimensional representations of the group actually. Okay, so summary that the the strongly interacting particles which we know now, mesons and baryons, could nicely fit into this group theoretical framework thanks to Gell-Mann. Okay. And we can actually go ahead and see actually there is more than this. Okay, so first thing is actually it's just treating them as it is, and then classifying them like what Mendeleev did. Okay, here the mathematics is a group theory. Okay, and that led to very profound understanding of these hadrons in terms of something much more fundamental. Okay, so why group theory is important in this context actually? Because in this, the exercise that we showed actually, it's not that we actually put all these particles in the fundamental representations. They are actually something like some kind of a tensor product of the representations actually. You take a tensor product of few representations and combine them, and you call them as actually a new particle, a new hadron. Okay, so that means in this entire setup, there is something which is building it, some building blocks. Those building blocks they combine together and produce this. So that's what this group theory taught us in this framework actually. So if it is only SU3 and fundamental representation, you could only accommodate only 3 particles, let's say A, B, C. Okay, but if you think all these things are actually some tensor product of various representations, then it says actually there is it's not actually single entity, but they are more like a composites. Okay, so that's what this group theory and this this entire quark model, not quark model, this this eightfold way actually taught us. Okay, using this nice idea, okay, Gell-Mann thought that it is possible that actually these hadrons that we see, okay, might have something which is common. Okay, something that is common, that by taking a tensor product of them, you can construct various hadrons actually. So that was his idea actually. So this is a very beautiful idea, because nobody could think that actually that okay, proton is just made up of some 3 quarks and things like that. It is because when we classify, you understand there is underlying mathematics tells you that it's a combination of something actually. If you want to make a doublet, triplet, these wave functions for these hadrons using this group theory, it's a tensor products that makes it actually. So that was the reason why Gell-Mann proposed that let's imagine there is some mathematical constructs like quarks and antiquarks, okay, and try to see whether we can actually understand this zoo of hadrons in terms of this mathematical constructs. For him at that time, it was not anything that actually jumps and talks and moves and things like that. Quarks and antiquarks were just mathematical constructs. It is like, if I want to write A is equal to B into C, okay, B and C are just simple mathematical terms. Okay, A doesn't have any life, B doesn't have any life. I am just writing A as B times C. Okay, it is as simple as that actually. So if you write A as B times C and something else as some other combinations of B and C, and if we could actually show that everything can be written in terms of B and C by some combinations, then you can say, okay, there is a nice mathematical entities called quarks and antiquarks that actually can, give you all the hadrons that we see in nature. So for him, they were just mathematical constructs, like, representations in group theory. Okay, they are just mathematical constructs. They don't have life. Okay, they don't interact. There is nothing. Okay, there's no physics. They are just certain, way of representing, elements of the group. Okay, different representation of the group. They all have same properties, but they look very different, talk different, and so on and so forth. Okay, as far as Kalman was concerned, they were not just mathematical entities, and we'll see actually they are also real actually. So the proposal was actually that baryon has to be made up of these three mathematical objects called three quarks, and then mesons had to be made up of quark and an antiquark. This antiquark sounds, very physics related actually, but this is actually the conjugate representation of SU2 or SU3. Okay, so you take a representation, put all these quarks in one representation, and you construct a conjugate representation. I call them as antiquark. Okay, so that's how. That's how this group theory enters. Okay, so to make it more precise, quarks and antiquarks are assumed to be constituents of hadrons and are spin-off particles carrying fractional charges. So this is the result that came out of this understanding from group theory, thanks to this classification actually. If we had not tried to classify these hadrons using group theory, I don't think we would have come up with this beautiful mathematical constructs before the experiments were actually able to show that this was indeed the case. Okay, so this was prior to experiments actually, as you can see. Okay, that's very nice about this entire physics. Even before experiments could see that there exist, these constituents. The Kalman and Zweig came up with a very beautiful idea of understanding these hadrons in terms of these mathematical constructs, and also actually give some life to them actually, calling them as quarks and antiquarks, assigning certain quantum number called spin and charges and so on and so forth actually. Okay, that was this work of this gentleman actually. So in simple terms actually, you can put, at that time actually, there were only three types of quarks that they could have needed actually. So U, D, and S, up quark, down quark, and strange quark. And they transform in the fundamental representations. So again, I'll go back and emphasize that the hadrons are not in the fundamental representations, okay, but they are in the higher dimensional representations or tensor product of representations. What is in the fundamental representations of this particle actually, this U, D, and S, they transform as a vector under SU3 group actually. This SU3 group is parameterized again by this exponential of alpha dot t, where alphas are the parameters, SU3 being group three of actually of 8 generators associated with it. Okay. SUN has n square minus 1 generators. So you need 8 independent parameters to actually specify an element of this group. That's all it means actually. And because it's a special unitary group, it has this nice property. And these generators satisfy Lie algebra, which looks very much like this actually. Okay, these F's are the structure constants. So they are completely antisymmetric because left-hand side is actually antisymmetric with respect to A and B. So these are the generators. They're called Kalman matrices in modern language. So, and what they could do actually, they put all this UDS in the fundamental representations, and the adjoint representations contain U bar, D bar, S bar. Okay, and the charge assignments under T, T3, hypercharge, strangeness, and baryon, they could actually give certain numbers so that actually they correctly reproduce hadrons with a specific electric charge or a baryon number or a strangeness. So we had seen actually that the entire classification of hadrons can be actually understood by just looking at the representations of this SU3, giving certain quantum numbers, like this. Okay, this is just put in by hand actually by looking at various properties of hadrons. Okay, good. So, of course, group theory again plays an important role. So if you want to actually get those hadrons that we put it in the sheet of paper as triangles and hexagons and so on and so forth, various representations in the YT3 plane, now you can actually realize them if you assume mesons are made up of quark and an anti-quark, baryons are made up of 3 quarks. Okay, if they are quark and an anti-quark, group theory tells you that you can actually express them as this product of two fundamental and conjugate representation. It becomes octet plus singlet one actually. So octet one will contain all these mesons. Okay, and group theory tells you how this can be combined actually. So you can see that pi plus is nothing but U bar U, and pi 0 is U bar U, and so on and so forth actually. So that you can actually, using this SU3 group, we can actually express the wave functions for all the mesons in terms of the wave functions of this quarks and anti-quarks actually. That was the first reduction. Okay, what is the fundamental building blocks? That question that everybody is asking. Okay, and similarly you can actually understand the singlets by combining these particles. What about baryons? Baryons are, as you know, that they are made up of quarks, anti-quarks, 3 types of quarks. Okay, they all can be identical or different. And again, how do I get that picture that I saw actually earlier as triangles and hexagons? That also can be understood if you look at the group theory of it. Actually, you just multiply the product of these 3 representations, 3 cross 3 cross 3. The Young tableau tells you that if you multiply 3 into 3, you get 3 star plus 6. And I multiply this combination with another 3, you get 1 plus 8 and 8 plus 10, and combine all of them, you get this actually. You get a singlet representation, 2 octet and 1 decuplet representation. So these are the ones that we saw earlier actually. So some of this, if you assume that we have these quarks, anti-quarks are the building blocks, or they are the ones actually that are the making these hadrons, or the mathematical objects that actually can be used to express these hadrons, then we have this nice explanation for this, this table that we prepared actually, how they were nicely fitting in actually. So it is, when the classification through eightfold was done actually, there was no real understanding why they were all fitting into this nice beautiful looking shapes, okay? These geometric shapes like a triangle or a hexagon and things like that. Why they were fitting, there was no answer to it actually. But now, thanks to this, this understanding of hadrons in terms of this mathematical constructs called quarks and anti-quarks, we could actually understand why that structure emerged. as an experimental, what do you call, exercise. You try to put them, in some way and see some patterns. That pattern emerged simply because there exist such, quarks and antiquarks that constitute these hadrons. Thanks to this underlying symmetry group, we could actually understand why they could be classified in the way that we see now. Actually, very good. So this is how baryons look like actually. So you can actually have baryons with spin-off with positive parity, and they all can be expressed in terms of this U, D, and S in a particular fashion. Similarly, the other type of hadrons, like the excited ones, 3/2 plus, they are not those days called fundamental particles. Okay, some excitations, you can also express them in terms of various combinations of these U's and D's and stage quarks. Very good. So this is something which you can take home actually. So summary, the classification of hadrons using group theory can be understood if you assume that the hadrons are made up of quarks and antiquarks. If they come with some specific spin assignments. Okay, and group theory tells you that this is possible actually. You can actually understand them. So this is the summary of the part that I wanted to show. Of course, every story has twists and turns. Here also there is a twist actually. While they were all working very nicely, there were many new hadrons that were actually discovered at that time, which they could not actually fit into this simply because there was something that was really not allowing, namely what is called the Pauli exclusion principle. For example, if you look at delta plus plus, you can take many examples of this kind. I'm taking this one as a simplest example. Okay, and using that whatever mathematics that we studied, SC3 group, you can express this delta plus plus because it is double plus. So you can express the wave function in terms of 3 U quarks, all of them actually placed up, up, up. Okay, and write down the wave functions. This is not a, it's a baryon, so it's a, it satisfies Fermi-Dirac statistics. Okay, and if you write down a wave function in terms of these 3 particles with all up, okay, quantum mechanics tells you that this wave function has to be completely antisymmetric because this is a half-integer particle. So it has to obey Fermi-Dirac statistics or quantum mechanics. Okay, but we all know that in this model, actually, all the spatial wave functions are symmetric. Okay, so we cannot construct anything which is antisymmetric. Flavor and spin part also is symmetric, as we can see. All the these flavors, they are all U type actually here. So if you have 2 different types, at least we can actually make certain combinations which could be antisymmetric. That is also not possible here. Okay, and spin here are all actually, so that is also not possible. So it's not possible to actually write down a wave function in terms of this, this mathematical constructs U's and D's in such a way that you can actually have a wave function which is fully antisymmetric. Okay, this was a problem. Again, of course, we all are physicists. We know we find always solutions to problems. Okay, so this gentleman, Hahn and Nambo and Greenberg and Gell-Mann, again, not from any experiments, okay, came up with a very beautiful idea of introducing new quantum number actually. So if you have problems, you introduce something. Okay, that will solve. Of course, it will have enormous consequence and you'll have to deal with it actually. So you don't take that lesson that if some problem, introduce new things. Okay, but this what they introduce as a new thing actually, of course, had a very important consequence. First of all, it solved the problem. If you introduce an additional quantum number, you can always actually use that additional freedom to actually make this wave function antisymmetric. You can always do this actually. Okay, so one such combination is actually put these indices, what they call new quantum number called color quantum number, introduce I, j, k, and I and j and k and run from 1 to 3. Okay, and then you can construct a combination of this along with this plus and up and so on and so forth. So this is some way of managing to write down a wave function that could be fully antisymmetric. Okay, so in some sense it's a birth of quantum chromodynamics because this is the one that actually helped later on actually to pin down what is the underlying gauge group to describe strong interaction physics. We'll talk about it a little later. So at this point, actually, I wanted to convince you that if I don't introduce an additional quantum number to this, whatever program that Kalman had sort of set it up for all of us to understand the large number of hadrons, okay, will be incomplete actually if I don't introduce this. So this was something that was introduced, and I think there are many more names because these are controversial things who actually first introduced this color, but that's not our interest now. So assume that there is someone who introduced, or some group of people introduced, and that really solved, the remaining problem in this. Okay, so in summary, that it's always good to classify. If your room is very dirty, very tidy, try to arrange it. Actually, you'll always find there is something very interesting hidden there. So that's some lesson that you learn actually. So in the process of classifying hadrons, people found out there were a lot of symmetries that we can actually explore to classify them, and that symmetries also help to understand more and more about what kind of dynamics that is going on inside in this system. Okay, and people like Gell-Mann and Zweig came up with a very nice idea of writing down in some mathematical terms called quarks and anti-quarks. Okay, certain entities could actually describe this pattern that they see, when they classified in like a triangles and hexagons and so on and so forth. Actually, so this was the first, and I would say, very good understanding of the structure of the hadrons, baryons, and mesons in terms of certain constituents. Actually, so far this is just a mathematical construct. Okay, there were no experiment which demonstrated that like the living objects, like there are some quarks and some anti-quarks. If you put them in a jar and mix it and you produce hadrons and so on and so forth. Okay, so there are no real experiment which these are some way of actually classifying the particles, hadrons. Okay, so you take it in that spirit. Actually, you don't think that Gell-Mann was a god who could actually break proton and could see these things. Actually, it's a very beautiful mathematical way of describing certain objects. Actually, but to really show that this is indeed the case, we need to do experiments. We need to actually make further progress. Actually, so that I think I will cover in my next set of lectures. Okay, so this is going to be my next part. Actually, this is where I'll stop using these slides. In the next class, I will use the board actually to describe how we can actually understand the structure of the proton by really performing an experiment, not classifying them. Okay, Gell-Mann's work was actually classifying them. Actually, the next part of the course, part of this talk is actually not about classification. It's about really doing an experiment with these hadrons. Take one of them and try to do an experiment and see whether something emerges actually. And you will see that actually what Gell-Mann and other people have actually imagined using mathematics, okay, are going to be true. Okay, so that's the next part of the course. So this is just advertisement for my next talk. Thank you.